Hi everyone and welcome. I'm very excited to introduce today's speakers, Dr. Lester Mackey. In normal non-pandemic working from home times, Lester's office is just a couple of doors down from mine, and our corridor conversations are one of the things that perhaps I miss the most work-wise. If you stroll by his office, you may find baked goods. He does eat muffins from the cafeteria. I hope he doesn't mind that I say that publicly. But also another feature of his office is the whiteboards full of things that I wish I could understand as well as he does. It is an absolute joy and a thrill to get to work with him. For those of you who don't know Lester, he's a statistical machine learning researcher at Microsoft Research New England and also an adjunct professor at Stanford University. He received his PhD in computer science and his MA in statistics from UC Berkeley, his Bachelor of Science in computer science from Princeton. And Lester's current research interests include statistical machine learning, scalable algorithms, high-dimensional statistics, approximate inference, and probability. Lately, he's been developing and analyzing scalable learning algorithms for healthcare, climate forecasting, approximate posterior inference, high-energy physics, recommender systems, and the social good. So without further ado, let's hear Lester's talk.
Hello everyone, my name is Lester Mackey, and today I'd like to talk to you about a remarkable technique. It's called knowledge distillation, and this is how it works. First, you train your favorite accurate classifier. This can be anything. It could be, say, a random forest ensemble of 500 decision trees. Let's call this the teacher model. Then you train a simpler model, called the student, to mimic the teacher's predicted class probabilities. This is typically much simpler than the teacher, so maybe just a few decision trees. Third step, that's it. There are actually only 2 steps. So let's see how this works in action. So here I've trained a 500 tree random forest teacher to predict income level from census data. It's pretty accurate, 91% AUC. And now I'm going to train a more compact student random forest to mimic this teacher. Here's what happens, and this is the first surprise. If I train this student model with 1 tree, I already retain most of the teacher's accuracy, already 89% AUC. And by the time I incorporate 10 trees, I've essentially matched the teacher's performance. But the remarkable thing here is that this model is much simpler to deploy. It requires 50 times less storage and computation at test time, and that makes it much easier to deploy in resource-constrained environments. Okay, so you might say now, why are we doing this 2-stage procedure? Why not just train a single decision tree or 10 decision trees directly on your raw data? Well, this is the second surprise of knowledge distillation. Quite often, when you train exactly the same student using the raw data, the performance is uniformly much worse. In this case, the 40-tree raw student, the student without knowledge distillation, performs about as well as the 2-tree distilled student. So these are some of the reasons why I'm excited about knowledge distillation, or KD for short. First, your simpler student often retains most of the accuracy of the teacher. This reduces your test time computation and your test time storage, and this is ideal for resource-constrained devices. Second, knowledge distillation is often much more accurate than training the same student from scratch. And there's a third reason too, and that's unlike many other compression strategies, the same 2-step strategy applies to any classifier. So you could apply it to your random forest, you can apply it to your favorite neural network or an ensemble, you can apply it to the output of AutoML, and you can apply it on any domain, tabular data, image data, language data, you name it. Okay, so now I've turned you all into knowledge distillation believers, but I do want to offer one word of caution. It's not the case that knowledge distillation always works quite as well as in this example. It often does produce excellent students, but often not as great as this. Here's a second example. In this case, I'm distinguishing 2 different types of websites, ephemeral and evergreen. Again, I've trained a 500-tree teacher random forest, and I'm going to mimic it with a compact student. What happens in this instance? Well, now with my KD student with 3 trees does recover most of the accuracy. I got about 80% out of the 82%. But you see in this case that the student never really converges to the teacher, even when I train up to 40 trees. And what's more, if I train my raw student from the raw labeled data, at some point it actually outperforms the distilled student. Once I have more than 20 trees in my model, I'm actually doing a bit worse than the raw student. So that's a little bit discouraging. and it raises some questions. First, how do we distinguish these two examples? And more generally, when should we expect KD to succeed or fail? And I think a little bit more importantly than that question is, can we do better? Can we enhance the performance of knowledge distillation? So we'll come back to that second question in a bit. But first, let's see what sort of answer we can get to the first question. Now, it turns out that the literature has a number of hypotheses and partial answers to the question, when should KD succeed or fail? Hinton et al. Conjecture that the reason why KD works is because the probabilities offered up by the teacher are more informative than the original raw class labels. Recently, Fuang and Lampert showed that linear students trained with knowledge distillation exactly mimic their linear teachers as soon as you have enough data. This means that your linear student performance will be exactly the same as your teacher performance, which means it could do well or poorly depending on how well or poorly the teacher did. Another line of work frames knowledge distillation in the learning using privileged information framework of Vapnik. The idea here is that the teacher is learning a better representation of the data that allows the student to learn at a faster rate. Finally, Mobahi et al. Very recently, in the specific setting of kernel ridge regression, showed that knowledge distillation acts like a form of regularization. This means this can improve generalization, it can improve test performance of the student, but can also harm performance depending on how much regularization is used. The jumping off point of this work is a recent observation due to Menon et al. Their insight was that the teacher's predicted class probabilities can serve as proxies for the true Bayes class probabilities. These are the conditional expectations of belonging to any, the conditional probabilities of belonging to any particular class, given knowledge of the feature vector X. The idea here is that if the teacher's probabilities accurately reflect the Bayes class probabilities, then student learning should improve. Building on this idea, in this talk, I'd like to cast knowledge distillation as semiparametric inference, also known as learning with nuisance. The typical goal in knowledge distillation is to fit an accurate, simple student model. And if we had knowledge of the true Bayes class probabilities, this would be greatly facilitated. This would be a much simpler process if we had knowledge of the true Bayes class probabilities, because then we could just train the student to mimic those Bayes class probabilities, and this is a noiseless regression, which is easier than the typical noisy classification problem. But of course, we don't know the Bayes class probabilities, so we'll treat them as nuisance. And you can view it in this light, knowledge distillation is essentially using a plug-in estimate of the Bayes class probabilities, which are the teacher's predicted class probabilities p hat. Now, this perspective is going to allow us to analyze the success and failure modes of KD, and it's also going to allow us to develop two improvements for enhanced KD performance to address the different failure modes that arise. And as a sneak preview, these enhancements can lead to much more accurate compressed students in practice. So going back to our failure example from before, if you apply your enhanced student to the same example, we find that we can exactly recover the teacher's performance with just 2 trees, and we can actually exceed the teacher's performance with 3. Okay, so now that I've whet your appetite, let's dig in. Knowledge distillation as learning with nuisance. So here's our setup. It's going to be a typical multi-class classification problem setup. I have n data points. I'll call them zi. Each zi consists of a feature vector xi and a label vector yi. Here I'm using a one-hot encoding in my label vector, and yi just indicates to which of k classes your data point belongs. Now I'm going to assume these data points come IID from some unknown distribution p. And here's our typical goal. Our goal is to learn a simple, accurate student scoring rule, f hat. F hat is going to take in a feature vector, and it's going to output a score for each of your k classes. And how are we going to capture simplicity? Well, we're going to restrict ourselves to have f hat belong to a function class, script f. And we're going to measure accuracy using a loss function. And this loss function will depend on those unknown Bayes class probabilities that I referred to earlier. We'll call those P0. Remember, these are just the conditional expectations of y given x, that is the conditional probability of belonging to any given class given the feature vector. All right. So here are 2 standard losses from knowledge distillation, 2 of the most popular. One is called the squared error logit loss. You can view it as essentially a regression onto the log probabilities outputted by the teacher. And the other is the annealed cross-entropy loss. And this looks a lot like the standard cross-entropy loss, but now I've raised my probabilities to a power, an inverse temperature parameter, and that smooths out the probabilities during training. Okay, so our goal is to fit a student f hat that approximates the optimal student, the student that minimizes the expected loss over the unknown distribution p. Now, I want you to note that this risk function, this expected loss function, is doubly intractable. First, as usual, we don't know the distribution over x, and second, we don't know p0. So what are we going to do? Well, it turns out that this sort of problem occurs all the time in semiparametric inference. There, the loss function is typically something like a negative log likelihood. The f0 is called the target parameter, and the unknown Bayes class probabilities are called the nuisance. And a standard approach to dealing with nuisance in semiparametric inference is simply to plug in an estimate of it. This is how it works. It's called plug-in empirical risk minimization, or plug-in ERM for short. Form some estimate p hat of your nuisance using your data set, plug that p hat into your loss, and then minimize the plug-in empirical risk, that is the average loss evaluated at p hat over your data set. And I just highlight here, this is using the same data. Okay, so now if I just substitute a couple of additional words into this recipe, if I plug in the words teacher and student, then it becomes clear that this plug-in ERM procedure is exactly the same as vanilla knowledge distillation. So, what is this perspective bias? Well, this is going to allow us to this perspective is going to allow us to answer the first question: when does knowledge distillation work? So here's a first answer based on a recent preprint with several of my colleagues. It's a theorem, and it's a fast rate bound for vanilla knowledge distillation. Let's break it down into pieces. First, a first term in blue is the student error, and this measures how well f hat, or the student you fit, matches the optimal student on test points. And we're going to bound the student error in terms of three quantities. One is just the factor 1 on n, that's going to 0 rapidly as your number of data points grows. The second quantity in red is a teacher error, and I just want to highlight that this teacher error measures not how well the teacher approximates p0 on test points, it actually measures how well the teacher matches the nuisance p0 on training points. And this actually makes a lot of sense because the only information we have about the teacher is its predictions on training points. And that's all that matters for student performance. Okay, there's one final term. This term in teal is a measure of the complexity or simplicity of the student function class that you chose, f. Now, at a high level, this measures how well loss differences approximate random noise. And specifically, it measures how well loss differences approximate random noise when your candidate student function f is close to the optimal student f0. I've actually given you the exact definition of this term here. It's called the critical radius of the localized Rademacher complexity, but I've purposely graded out so that those of you who don't care don't have to read it. Okay, one thing you should take away about this term, though, is that there are tight bounds on this quantity for many different function classes f. So it's the size of this parameter is going to be roughly 1 over n for parametric function classes, VC classes, and various kernel classes. Okay, so those are the major pieces of our bound. What's the takeaway? This theorem tells us that vanilla KD works whenever your teacher approximates P0 well on the training set, and noiseless student regression is relatively simple, as measured by delta n. And I also want to highlight that this result applies to the standard KD losses that I mentioned earlier, the squared error logit loss and the annealed cross entropy. And it applies whenever you have bounded f and log p. Okay, so that's great. That's a pretty satisfying answer for when does knowledge distillation work, but we saw in our example that KD doesn't always work. So when does it fail? Well, looking at the same result, we might guess that KD fails when the teacher is approximating P0 poorly on the training set. And this actually suggests two different failure modes for knowledge distillation. First, we'd expect KD to fail when the teacher is underfitting. And this could happen if the teacher's model is misspecified, if its function class is overly restrictive, or if it's just been insufficiently trained. On the flip side, this could also happen if the teacher is overfitting. That is, even if p hat, the teacher's probabilities, approximate p0 well on the test data, if they don't approximate p0 well on the training data, knowledge distillation may still fail. And this happens all the time in training very rich and flexible teachers, because the teacher is often overconfident on its training point and hence miscalibrated. So technically these are just guesses, because this bound is only an upper bound and not a lower bound. And so what I'd like to do next is to give you some simple lower bounding examples that confirm that indeed KD does suffer from both teacher underfitting and teacher overfitting in practice and in the worst case. Okay, so first let's explore the impact of teacher underfitting on KD. To do this, I'm going to instantiate a particular classification problem and show you that underfitting is a problem. In this problem, P0, the base class probabilities, and F0, the optimal student, are going to be constant, independent of X. So this is a pretty simple problem. Our teacher is just going to be ridge regression. So it's going to form this ridge regression estimate. It's going to use some parameter lambda, the regularization strength, and that regularization strength is going to introduce some bias, which in turn will introduce the underfitting phenomenon. Okay, we're going to use our standard loss from knowledge distillation, squared error logit loss. And now it turns out if your vanilla KD student, training just a constant F hat student, satisfies this bound. It says that the student error is lower bounded by the teacher error. And in this case, the teacher error has a slow rate of convergence, at least 1 over square root n. A couple of things to highlight about this. First, this lower bound matches their upper bound up to a constant. That's great. It means that that term is necessary, that teacher error term is necessary. And the main takeaway is that vanilla KD is not robust to teacher underfitting. In the worst case, if your teacher underfits, your student will underfit too. Now, a bit later, I'm going to introduce an enhancement specifically to address this problem. We call that loss correction. And as just a sneak preview, it turns out that enhanced KD with loss correction actually satisfies a very nice fast rate of convergence. So 1 over n rate of convergence, even though vanilla KD is at best a 1 over square root n, produces at best a 1 over square root n student. Okay, but we'll come back to that in a minute. Next, let's consider the impact of teacher overfitting. Again, I'm going to instantiate a specific classification problem to show you that overfitting is a problem in the worst case. Here, our P0 is going to depend on X, so that can be quite flexible. But our F0 is still going to be constant. So I just want to match the best constant prediction rule, the expectation of log P0. So the student is still very simple. Now in this case, we're going to use a different sort of teacher. We're going to use a teacher that exactly interpolates the labeled data, but still generalizes well. Specifically, we're going to use a kernel smoothing estimator that was studied by Belkin et al. And in this case, because the teacher exactly interpolates the labeled data, and the labels are different from P0, they're equal to P0 on average, but not in reality, the teacher's training error is terrible. Its training predictions, P hat, are terrible. They don't match P0 at all. They don't converge. Meanwhile, Belkin et al. Proved that the teacher's test error is great. It converges rapidly with this particular rate that I've shown you here. Okay, so again, let's break out our squared error logit loss. Let's train our vanilla KD student with a constant function class. And what we find is that our KD student is now inconsistent. And it's inconsistent for exactly the reason we'd expect, because its test error is lower bounded by the teacher's training error. This again matches our upper bound up to a constant. The teacher's training error in this case is order 1. It's not consistent. It's bounded away from 0. And what's the takeaway? Well, the big takeaway is that vanilla KD is not robust to teacher overfitting either. Now in a few moments, I'm going to introduce a second enhancement for dealing with teacher overfitting. It's called crossfitting. And it turns out that enhanced KD with crossfitting actually inherits the teacher's test error instead of its training error. So in this case, if we just employ crossfitting, we'll get the convergent rate, the same convergent rate that we saw for the teacher, and we don't have to worry about the fact that it does a poor job of approximating P0 on the training set. Okay, so what have we done? We've identified two different failure modes of KD, one due to teacher underfitting and another due to teacher overfitting. And what I'd like to do next is introduce two different KD enhancements that get around these two different failure modes. So we're going to introduce loss correction to deal with teacher underfitting and crossfitting to deal with teacher overfitting. So let's start with crossfitting. Okay, so we're trying to fight teacher overfitting. And the crux of the overfitting problem is that the student only observes the teacher's training set predictions. And as we know, training set predictions are susceptible to overfitting. So how can we deal with this? Well, a natural idea is to employ sample splitting. Let's just train the teacher on most of the data, but not all of it. We'll hold out a fraction, and we'll use that last fraction of the data to train the student. Now, this actually would solve the problem. This would solve the overfitting problem. But it has a downside. The downside is that the student's accuracy is going to suffer from having reduced training data. So here is a more effective idea that's often used in semiparametric inference. It's called crossfitting. Here's how it works. It's a bit like cross-validation. So first you take your data set and you split it into B batches. And then for each batch, you're going to fit a different teacher estimate on all the data except for that batch. We're going to call each of those teacher estimates P hat T. Now you're going to have your student minimize what we'll call the cross-fitted risk. And importantly, in this cross-fitted risk, each teacher estimate P hat T is only queried on its held out points. It's only queried on the points from its held out batch. And so that solves the overfitting problem. Now we're only observing the teacher's test predictions instead of the teacher's training predictions. But it also solves the downside of sample splitting because now the student is going to be trained on all n data points. So a natural question, does this work? Well, here's another fast rate bound from a recent preprint. Let's break it down again. It actually looks pretty similar to the bound that we proved for vanilla KD, but it has a couple of very small differences. Small, but important. First, the teacher error. Before, the teacher error measured how well the teacher approximates the nuisance on training points. Now we have a teacher error that measures how well the teacher matches the nuisance on test points. This is exactly what we want. We're typically using teachers that we know are good on test points, and we want to inherit their test error. This bound says, okay, now the student is inheriting the teacher's test error. Another small difference is that the complexity parameter now depends on P hat T instead of P0, but that's just a minor difference. So what's the big takeaway from this result? Well, now by using crossfitting, we have robustness to teacher overfitting. We don't have to worry about its training set performance any longer. Okay, so let's see CrossFit KD in action. So here's one of the examples that I showed you at the very start of the talk. Before, we noticed that if you're training your student without KD, it's not great, considerably worse than the teacher, even when you train it up to 40 trees. Meanwhile, we saw that vanilla knowledge distillation with 10 trees essentially recovers the teacher's performance. That's great. It has that's excellent compression from vanilla KD. Now there's a new curve on the plot, this green curve, and that's CrossFit KD. That's the only difference between this and vanilla is whether we're using crossfitting or not. And now we see that we basically get uniform improvements in the teacher's and the student's accuracy. And in particular, we recover the teacher's performance with just 3 trees instead of 10. On top of this, by the time we incorporate 10 trees into the CrossFit student, we're actually performing better than the teacher. You can see that the green curve is going above the teacher's line. Okay, that's fantastic. Here's another example. Similar setup. Here, if you train your student without knowledge distillation, it's not great. It's still uniformly worse than the teacher up to 40 trees. Meanwhile, the vanilla knowledge distillation is just barely catching up to the teacher around 40 trees. It has about the same AUC at 40 trees. Meanwhile, if we introduce crossfitting to deal with overfitting, we recover the teacher's performance with just 5 trees. So again, we're getting a excellent 100x compression using crossfitting. Now, here's the failure mode example that we saw at the beginning of the talk. There we noted two interesting things. First, neither the student with KD nor the student without KD is very good. Without KD, after 40 trees, we get to about 0.81, 0.82 accuracy. Still worse than the teacher. Still about 0.01 worse than the teacher. The student actually, the KD version of this student actually does a bit worse. So with 15 trees, it gets close to the 40 tree version of KD, but it never quite improves. And at some point, the student without KD overtakes it. Meanwhile, just introducing crossfitting, just dealing with this teacher overfitting problem, we can recover the teacher's performance with just 2 trees, and we can actually exceed the teacher's performance with 3 trees. So we're getting much more compression and actually matching the original teacher's performance. Finally, I'll give you one more example. Here's a case where the student without KD isn't great. At best, it recovers 0.7 accuracy with 40 trees. But the student with KD is actually even worse. It's actually doing a terrible job in this instance. And this seems mostly due to overfitting. And so even with 40 trees, it has worse accuracy than the student than the student without KD. Meanwhile, the CrossFit student, although it never quite catches up to the teacher, it can at least match the without KD student accuracy using just 5 trees instead of 40. So we're still getting a significant amount of compression, even though in this case, none of these techniques catches up to the teacher. Okay, so in each of these examples, the main problem was overfitting. Our teacher was quite accurate on the test data. It was less than calibrated on the training data, and so we needed to deal with overfitting. But now let's go back and explore the underfitting problem. So fighting underfitting with loss correction. So the crux of the underfitting problem is that KD relies wholly on the accuracy of the teacher, and this is true whether or not you apply crossfitting. And in particular, the student suffers when its approximation p hat of p0 is a poor approximation. Now, we can think about replacing the loss at p0 with the loss at p hat as a 0th order Taylor approximation of the loss. And when you view it in that light, a natural thing to try is a higher order Taylor approximation. Perhaps we could use a first order Taylor approximation instead, and that would lead to a better estimate of the unknown loss. So this is what the ideal first order correction would look like. You'd take your original plug-in loss of p hat, you'd add in a gradient term that depends on the difference between p0 and p hat. Now this would be a great idea if it were implementable, but of course we don't know what p0 is, so we can't use this. But we could imagine estimating this quantity, and in fact we could obtain an unbiased estimate of the quantity if we recall the fact that y has p0 as its conditional expectation. So the expectation of y given x is p0, so this unbiased estimate that I've drawn here, where I've replaced p0 with y, gives us one way of approximating that first order correction. Okay, great. So it turns out that this construction that we just developed produces what's called a Neyman orthogonal loss in the sense of Foster and Serganis. And all we need to know about that for this talk is that this means that this loss function is more robust to errors in p hat. That is, it's first order insensitive to errors in estimating p0, which means that our student will be hurt less if p hat is a poor estimate of p0. So that's exactly what we're looking for. And it also turns out that this unbiased first order correction has a very simple form for standard knowledge distillation losses. So here's an example with our squared error logit loss. The gradient of the loss decomposes into 2 parts. One part is linear in f. That's great. That means that gradient updates are going to be simple. It also means that it doesn't affect the convexity of your original problem. But it also has the second term. It has the scaling, which is a 1 over p hat scaling. And this term is a little bit scary. Like 1 over p hat, that seems like a strange thing to have, especially when p hat can be close to 0. And indeed, when p hat is close to 0, the variance of this loss function can explode, and it will explode. We'll see this in our experiments. So we perhaps don't want to go all the way to, perhaps we don't want to employ this unbiased estimate directly, even though it has this nice name and orthogonality property. So to give ourselves a little bit more flexibility, we're going to introduce a tunable correction matrix, which we'll call gamma, to trade off between the bias of the 0th order correction and the high variance of the first order unbiased estimate. And when we introduce this parameter and we produce this new loss function, we call this loss correction, or gamma loss correction. Now, in practice, we're going to combine this with the crossfitting approach that we just discussed. So crossfitting plus loss correction together give us what we'll call enhanced KD, enhanced knowledge distillation. And the only difference here is that instead of fitting a single gamma, we're going to fit a different gamma t per batch, in the same way that we fit a different p hat t per batch. Okay, let's see enhanced KD in action. First, let's understand when it works. Here's another one of these fast rate theorems. Again, it looks like the theorems we've seen before, but there are going to be a few extra terms this time, so let's go through it slowly. First of all, we have our standard teacher error term, but now it's raised to the 4th power instead of the 2nd power. This is a good thing. This means that the teacher's errors have smaller impact on the student. This term is going to be small even when the teacher converges very slowly. Before, the teacher needed to converge at a 1 over square root n rate in order for the student to have a 1 over n rate at the end. Now, if the teacher's error is 1 over n to the 1/4, we still get a 1 over n rate at the end. So this gives us that additional robustness to teacher error that we're looking for. Now, we also have some new terms in our bound. The first we'll call gamma bias. This term is exactly 0 when you plug in the best orthogonal choice of gamma, that 1 over p hat that we discussed before. More generally, this term is a doubly robust product of two different errors. The error in gamma hat, how well does gamma hat approximate 1 over p hat, and the error in p, how well does p hat approximate p0. Second, to counter that term, we have what we can call a gamma variance term. This term is exactly 0 when gamma is 0. Recall that gamma 0 means we're just using the original 0th order plug-in loss. We're not doing any correction. If you instead plugged in the optimal orthogonal value, 1 over p hat, you'll see that this term can blow up, especially because p hat can get small. And so, in practice, we want to trade off between this bias and variance term when picking our gamma hats. So what's the takeaway of this result? The main takeaway is that enhanced KD both avoids teacher overfitting using crossfitting and mitigates teacher underfitting by choosing gamma to balance between bias and variance. In practice, we're going to minimize a pointwise estimate of the bias variance terms in this theorem. So this is the exact program that we minimize. This is the exact way that we select gamma in our experiments. We introduce a variance term, a bias term. We trade off using a hyperparameter alpha, and we use that to pick our gamma. All right, let's see this on a few examples. Now here, in this case, our setup's going to be a little bit different from our past examples. We're going to use a fixed student, and we're going to vary the complexity of the teacher. The reason why we're varying the complexity of the teacher is that we want to explore what happens when the teacher starts to underfit. So here, in all the experiments, the teacher is going to be a 100-tree random forest. The student is going to be a 10-tree random forest, but we're going to vary the maximum depth of the teacher's trees. So you can think of the maximum depth as essentially a constraint on how many variables the teacher can use when making its classification. In particular, a depth 1 tree can only use a single variable to make its classification. And so what do we see from this plot? Well, first we see that indeed our teacher is underfitting. How do we know? Well, when the teacher has larger depth, it's doing better. When it has smaller depth, it's doing worse. We specifically constrained its flexibility here, so it's missing out on some of the accuracy that it could have gotten from larger depths. Okay, that's takeaway 1. Takeaway 2 is that at high depths, we're basically back into the setting we were in before. The teacher's doing a good job. It's accurate. It has good test error. And what we see roughly is that every variant of knowledge distillation is much better than not using knowledge distillation at all. That's the blue line here. This is the student without knowledge distillation. Okay, but what's interesting here is what happens for low depths. At low depths, the enhanced KD student, this is the student that has loss correction, actually does better than the teacher. And it's actually outperforming the teacher because the teacher is just so bad here that our student is learning I should really be trusting my labels and not the teacher in this regime. And so we end up with a student that does better than the teacher for all low depths, and then eventually just performs as well as standard distillation for higher depths. All right, here's another example where we can see both over and underfitting in action at once. Again, our teacher is underfitting when it has small depth. It has good accuracy when it has higher depth. And we see a few different regimes. At low depths, again, the enhanced student is outperforming the teacher, making use of that loss correction that we've introduced. In the middle depths, in the mid depths, you might say, all of the KD students are performing about the same, and they're all doing much better than a student trained without knowledge distillation. And then finally, for high depth, something very interesting is happening. Vanilla knowledge distillation starts to do worse, even though the teacher is getting more expressive. And that can actually be explained with overfitting. This is a case where our teacher is getting more and more expressive. Its accuracy isn't really improving, but it's basically about the same as it was before. And what's happening is that its training set probabilities are becoming miscalibrated. And because the KD student, the vanilla KD student, only sees those training set probabilities, it starts to do worse. Meanwhile, the enhanced and CrossFit students are only looking at test predictions of the teacher, and then so they maintain their performance throughout this plot. Great. One more example. Here's a case where the student without knowledge distillation is actually better than the teacher when the teacher is too constrained. So that's very interesting. And again, we have a few different regimes. We have low depths. And at low depths, what do we see? We see that, well, the student without knowledge distillation, as I said, is better than the teacher. It's relying on the labels. The teacher is so constrained that just using the label data is better. But our enhanced student does even better. By combining the information from the teacher and the labels, it can outperform the student without knowledge distillation. Meanwhile, for mid-depths, we see that all the knowledge distillation students are doing better than the student without knowledge distillation, and the enhanced student is doing particularly well. And then for the highest depths, enhanced is again better than vanilla. Vanilla is starting to the teacher is starting to overfit, and the vanilla student is inheriting that overfitted teacher error. Okay, so this is great. And now all the examples so far have been focusing on random forests on various different tabular data tasks. Here's an example on image classification using residual networks, a certain type of deep neural network. Here we're using CFAR10. This is a 10-way image classification task. The student is a depth 10 ResNet. The teacher has varying depth ranging from 14 up to 56, also a ResNet. And what can we take away from these plots? Well, first, we see something interesting. The depth of the teacher network is increasing. Typically, we associate that with higher accuracy, although, the accuracy is kind of bouncing around. It's not much better with 56 than it was with 20. And so what do we see with the student? The vanilla student is actually getting worse as the teacher's depth improves. What could explain this? Well, a natural guess would be the student is suffering from overfitting. The teacher ResNet has increasingly more miscalibrated training set probabilities, and the vanilla student is suffering as a result. An easy way to test that hypothesis is just to substitute a crossfitted student for the vanilla student. And when you do this, you see that indeed it maintains essentially the same performance across all teachers' network depths. So it effectively corrects for this overfitting phenomenon. Then on top of that, the enhanced student is benefiting from loss correction, so you get additional nice gains on loss correction. And on this left plot, I've been focusing on test accuracy, but on the right plot, you can see an even more extreme difference in terms of test loss. There, the enhanced and CrossFit students are doing as well, or in some cases better than the teacher in terms of test loss. Here, the loss is just standard cross entropy. But meanwhile, the KD student is doing remarkably worse in terms of test loss due to overfitting. Now, this is also a good setting for exploring the effect of that trade-off parameter alpha that occurs in our loss correcting objective. So recall that the way we pick gamma hat is the trade-off between this bias and variance term, and the trade-off is determined by this alpha parameter. When alpha is very big, when it approaches infinity, we end up recovering the optimal Neyman orthogonal loss, the optimal but high variance Neyman orthogonal loss. This is essentially just setting gamma equal to 1 over p hat. And we see that with these extreme settings of alpha, our test accuracy drops off precipitously and our test loss grows precipitously. Why is this happening? Well, our loss is very high variance, the gradients are high variance, and this leads to very unstable training of our neural networks. Meanwhile, if you set alpha equal to 0, then you're doing no loss correction. You're just using the standard plug-in loss from vanilla KD. And what we often find is that there's a sweet spot between these two extremes. It's here in the plot about alpha 10 to the minus 2, and that leads to the best performance overall. Better than no loss correction, but also better than the orthogonal loss. Okay, so what have we accomplished so far? We've framed knowledge distillation as learning with nuisance. We use this to prove that knowledge distillation succeeds whenever the teacher's training set probabilities are accurate and noiseless regression is particularly simple. And we also use this to identify two knowledge distillation failure modes, one due to teacher overfitting and the other due to teacher underfitting. And we developed two distinct KD enhancements to mitigate these two distinct failures, crossfitting for overfitting and loss correction for underfitting. And you can learn more about all of this, knowledge distillation as semiparametric inference, in our paper called Knowledge Distillation as Semiparametric Inference. Here also is our code for replicating all the experiments I showed you. But I'd like to spend a little bit of time now talking about future directions, because I think there are actually many opportunities for future development. First, can other tools from semiparametric inference improve KD? I've introduced and adapted two different tools, crossfitting and orthogonal loss correction, to gain KD enhancements. But there are other approaches to improving upon standard plug-in estimation. One good example is the targeted maximum likelihood framework of van der Laan and Rubin. And so a natural open question is, can these tools also be ported to the KD setting, and what sort of benefits do we gain from that? Second, there's this remarkable phenomenon that self-distilled students often outperform their teachers. Self-distillation just means use the same student model as your teacher model. So instead of training a simpler student, use exactly the same class of random forest or decision trees to mimic your teacher. And the shocking thing that happens when you do this is that quite often the self-distilled student is better than its original teacher. So what explains that? What explains that surprising success? And finally, a number of empirical studies have showed that synthetic data augmentation can often improve knowledge distillation, even when it harms the original supervised learning task. So let me give you an example of that. This is an example taken from a study performed with my collaborators Rishan Liu and Niccolo Fusi. And here again is one of the same tasks that we studied before. We're distinguishing ephemeral websites from evergreen websites. I trained a 500 tree random forest teacher. It has 0.889 AUC. If you use just vanilla knowledge distillation, you get back the yellow-orange curve here. It has about 0.86 AUC. But if instead of training on your training data, which is what you typically do in knowledge distillation, instead of training your student on the training data, if you use synthetic data, that in this case is generated from a generative model called a generative adversarial network, then you get a big boost in performance. You get a 0.02 boost in performance, and you essentially match the teacher's performance with a single tree. So a 500x reduction in storage and in computation. So that's surprising. This comes from some work from 2018 called Teacher-Student Compression with GANs, that is with generative adversarial networks. And there are a number of other experiments in this paper that have similar conclusions. Here's another one with a different task. Here you're trying to distinguish different signals from a gamma telescope. And on the left, you see the same conclusion, that using synthetic data to augment your student training can lead to improved performance for KD. But what's striking about this pair of pictures is that on the right, if I take the same synthetic data and I use it to retrain the student on raw labels, with raw labels instead of using distillation. So if I don't use distillation, I just use synthetic data with raw labels, I find that the same augmentation actually impairs student performance. So you're better off just using your original training set than augmenting with that same GAN data. So this is a little bit surprising. Like, why is this happening? And I should just say quickly, for those who don't know, what are generative adversarial networks? What are GANs? GANs are pairs of networks that are being trained to compete with each other. So one network is learning how to take random noise and turn it into a reasonable looking feature vector, like an image. And the other network is learning to distinguish between these fake images generated by our new generator and real images. And they compete with each other, and as they compete with each other, each one learns to be better. One learns to be better at generating images, the other learns to be better at discriminating fake images from real ones. In particular, we use auxiliary classifier GANs in these experiments. And so I just wanted to highlight that the same sort of phenomenon happens when you're using not random forests, but deep neural networks. So here we're back to our CFAR10 image classification task. Here we have a teacher. It's a network teacher. It has 78% accuracy. If you don't do any knowledge distillation, you have 66% accuracy. If you use vanilla KD, you boost that up to 71%. And again, if you augment with GAN data, you get another very large boost to 76%. So the same sort of phenomenon we were seeing before. And a similar sort of surprising phenomenon occurs here. If you look on the left, here I'm showing you what does the student test accuracy look like as a function of how much GAN data I spike in. The blue star represents using just the teacher's training data. The orange star represents using only GAN data, and we see in this case using only GAN data is actually better than using the teacher's training data. Why could that happen? Well, one way to think about this is that it's another way to deal with the overfitting phenomenon. Instead of looking at the teacher's training set predictions, we get to look at the teacher's test set predictions on points that the teacher did not train on, and those probabilities are typically more calibrated. And so that's why we see this boost here, and we see an additional boost from interpolating between the two, using a mixture of the teacher's training data and this synthetic GAN data. So that's what we see when we're doing distillation. But if we're just working on the original supervised learning problem, and we try to train a student on raw labeled data using either the teacher's training data or GAN data, we see that GAN data actually just impairs performance. The more GAN data we use, the worse the student gets. And so whatever explanation we have for why synthetic data works, it should be able to discriminate between these two different tasks. Now, I also want to highlight that doing this sort of synthetic augmentation with a GAN can also complement standard types of image augmentation. So quite often in image augmentation, you'll add in additional images that have random flips or that change the hues or saturation values. And so this plot is showing you that if you combine GAN augmentation with standard augmentation, you get even more improvement. This brown dot over here represents just standard augmentation. This brown dot up here represents the best combination of standard and GAN augmentation. Finally, I want to note that the quality of your GAN data does matter. So this isn't a magic bullet. It won't always work. If you pass in terrible GAN data, your knowledge distillation student is also going to be terrible. And so this is just showing you a plot where the x-axis is varying the quality of the GAN. It's getting better as you move across the axis, and the y-axis is showing you the accuracy of the trained student. And indeed, if you use a really terrible GAN, the student will have terrible accuracy. And in fact, these knowledge distillation is sensitive enough to the quality of the GAN that you can imagine using it as a measure of the quality of your synthetic data. And this is exactly what Rishan, Nicolo, and I did in our teacher-student compression work. We created what we might call a teacher-student compression score that essentially just measures the test accuracy of a student distilled with synthetic data, and it uses that test accuracy as a quality measure. It tells you how good your GAN data is. It's good if it makes if you can distill a student well using it. And you can do it in a way that's efficient, where you just train your student network for a single pass through your data. And you might compare that to other standard measures like the inception score. So here's just a quick comparison between this teacher-student compression score and an inception score. On the left, you see real data from CFAR10. In the middle, you see GAN data from a well-trained GAN that's pretty faithful to the real data. And here on the right, we've actually constructed an inferior GAN that has all sorts of very evident artifacts that make these images look atypical. But these evident artifacts actually confuse the inception score. The inception score has high confidence for these images, so it declares that these are actually of better quality than the well-trained GAN images. Meanwhile, the compression score, which is based on actual test performance on real data, notes that this inferior GAN data is worse than the well-trained GAN because it's more difficult to train a student, to distill a student using this data. And you can learn more about that in our paper, Teacher-Student Compression with GANs, and there's code replicating this experiment there as well. So this leads to the last question that I want to leave you all with, and hopefully this will seed some of our discussion. What characterizes a good generative model for KD? We've seen that GANs can lead to good KD performance, but sometimes they don't. If your GAN quality is terrible, it won't. Past work has shown that synthetic data based on a procedure called MUNGE, which is a tailored generative model for tabular data, can also lead to great student performance. How do we know? How do we know if a model will work well? How to explain its failure modes? That's the last final question I'll leave you with. And thank you for your time.